Hello everyone, thank you for coming to listen to my talk. I'm Kangmuk Lim from UNIST, and this work is about Approximate Quantile for data center telemetry monitoring. It is collaborated with UNIST, Microsoft Research, Oracle, and Facebook. Cloud data centers are now everywhere. It is well known that 90% of companies are on cloud, and cloud data center will process 94% of workloads in coming 2021. As a result, it is very critical to provide reliable data center more and more. This is high-level flow of reliable data center. Data center monitoring system measures various key performance indicators and perform crash detection. If any crash is detected, it takes a recovery action. Whole this pipeline must be done in timely manner. To satisfy this requirement, it is common to practice streaming analytics. Streaming analytics is based on different types of operators, and in this paper, we are focusing on quantile operator, which is widely used to detect normal and abnormal behavior for the monitoring system. This figure shows the case that we are computing 4 different quantiles. Non-high quantiles such as 0.5 quantile represent the normal behavior, and high quantiles such as 0.99 quantile or 0.39 quantile represent the abnormal behavior. However, by nature, quantile operation is resource intensive since it has to keep all data points in sorted order. As a way of solution, we consider to apply approximate quantile rather than exact quantile calculation. We propose a new quantile approximate methodology called AOMG. There are 2 following contributions. The first one is we are overall providing better approximation for several important performance metrics. AOMG has the highest throughput, the lowest space usage, and especially the lowest error in terms of relative value. And secondly, we bring out a new accuracy metric for quantile approximation customized for data center telemetry monitoring use case. That accuracy metric is value error, and that is very different from traditional accuracy metric, which is rank error. In this slide, in the next few slides, I will show you why the value error is more important than the rank error. To explain it, let me give you a real-world example. Microsoft Pingmesh. This is network latency measurement and analysis system for Microsoft large-scale data center. The purpose of this system is to locate the network reachability issue among different components in data center. Looking at a bit more detail how it works, data centers have network hierarchy inside. Pingmesh collects inbound and outbound latency data between servers, and then quantiles are computed using grouping on this network hierarchy, and locate which switches or which machines generate issue. Using high quantile such as 0.99 quantile, Pingmesh draw part-to-part pairwise latency heat map to visualize network condition. Green one here indicates low latency pair, and the red one indicates high latency pair. The left figure shows a pattern of a red cross, and it corresponds to a path set. So it shows high latency network issue within the path set. Right figure shows that the network latencies with the path set within the path set are normal, but there are high latency issue in cross path set. This visualization is utilized by network management team, developers, and customers regularly to see if the network is fine. Accurate heat map lets you easily spot where the network issue is generated, as you can see. Therefore, it is very important to get accurate quantile, which is close to exact quantile, to draw heat map correctly. In order to estimate quantile accurately, we will take online distribution of telemetry data into account. This blue box is corresponding to non-high quantile, and this part has many recurring value, which represent normal status. And the red box is corresponding to high quantile, and this part has substantial skewness, which represent abnormal status. Under this distribution, low rank error doesn't guarantee low value error always. This graph shows impact of a rank error. Here R is the rank of each quantile, and 0.2 epsilon means 2% of rank error. At 0.5 quantile, 2% of low rank error leads to 2% of low value error. However, at 0.99 quantile, 2% of rank goes to unacceptably huge value error. This is because they have low data density in the tail part, and its distribution has long tail. Now, let me introduce the detail of AOMG method. It has two parts. One is for non-high quantile, and the other one is for high quantile. And high quantile is divided into two different techniques again. Let's look at the non-high quantile part first. The key of efficient non-high quantile approximation is exploiting self-similarity. If there is self-similarity, data distribution across different time frames are similar. So their calculated medians are similar across time frame as well. With this observation, we can get accurate quantile approximation using relatively simple two-level hierarchical method. Before explaining the method, let me define some terminology first. So there is a window, and you want to estimate the quantile of this window. And this one window consists of a number of sub-windows. In this method, approximation is calculated by getting the exact quantile from each sub-window in the first level and applying mean operation in the second level. After one time step, the oldest sub-window will be discarded and the summary of a new sub-window will be added. Because we only maintain summary per sub-window instead of entire data, we could achieve much lower space usage and calculate quantile faster than exact quantile operation. This relatively simple method shows high accuracy for non-high quantile thanks to self-similarity. But there are two complementary cases that previous method doesn't work. They are corresponding to calculating very high quantile. First case is statistical inefficiency. Statistical inefficiency happens when there's not enough data point in each sub-window for calculating given quantile. For example, when a sub-window contains 1,000 data points and you want to calculate 0.39 quantile, then you end up with relying on only two largest value, and that is statistically very not robust. Second case is Birdsey tail. Birdsey tail occurs when there's high skewness of large value in a window. So one or two sub-window has almost all the largest value of a window. For each case, we're proposing two different techniques exploiting collected low data point. Type K merging to tackle statistical inefficiency caches largest value from each sub-window. Red diamond is large value that affect high quantile result. So now you have enough largest value to calculate high quantile because you already cached them. And you merge this cache value and answer query quantile. The reason this method works is that large values are likely to be distributed across different sub-windows. To handle versatile, we perform sample k-merging, which does interval sampling from each sub-window to capture the distribution of the largest value of a window. However, there's a challenge here. Here, already existing versatile can be expanded outside a window. Or a new versatile can join a window. And also after existing versatile is expanded from a window, a new versatile can appear suddenly in the middle of a window. It can happen because versatile is relative. If a certain sub-window becomes to contain all largest valuable window after previous old versatile exceeds the window, then now this new window sub-window becomes versatile. As you can see, because of this unpredictability of versatile, we have to do sampling from all sub-window. And then after that, you merge it and answer target quantile. If we combine all proposed techniques together, first, when there's distinctive distribution in the sub-window from adjacent sub-window, then it takes sample k-merging. If not, it checks there is no too small data point in a sub-window to answer given query quantile. If it is, it takes top k-merging. If no, it just use non-high quantile method. We evaluated AOMG on Trill streaming analytics engine and run these queries. And we used two data sets in the paper, but this presentation will just focus on Microsoft Pingmesh because of time limitation. And we compare AOMG with CMQS, random, and moment sketch, which are all rank error based method. Let's look at the accuracy first. For the left figure, x-axis showed 4 different target quantiles, and y-axis shows rank error. So the lower is the better. As you can find in the left graph, all competing policies provide low rank error successfully, which is satisfying their design objectives. We find that AOMG is also delivering low rank error. But the main difference comes when we are comparing value error. On the right figure, we are comparing value error for the same quantile across policy. We see the clear difference in delivering very high quantile. Only AOMG successfully falls within 5% value error. Except for AOMG, all other methods fail to bound value error below 5%, especially for 0.39 quantile. Now, let's compare throughput between AOMG and other rank error based method. We pick CMQS only because CMQS has the highest throughput among rank error based method. X-axis shows different policies, and y-axis shows throughput in million data point per second. So the higher is better here. On the x-axis, you can see 3 different CMQS, and this is because we put variation on epsilon for CMQS. This is for looking at a range of rank approximation bound. CMQS has clear trade-off between throughput and accuracy. When setting the epsilon low, it guarantees low rank error. However, in the case CMQS will become too slow. On the other hand, when setting the epsilon too high, it shows relatively high throughput, but in that case, obviously you have to sacrifice accuracy. However, AOMG achieves the high throughput and also keeping value error low. This shows the effect of a top K merging technique. X-axis shows different sub-window size. Those are relatively small size that causes statistical inefficiency. And the term fraction here defines how many largest value data point you will cache. With top K merging technique, AOMG successfully bound value error around or below 5% for all appearing small size of subwindow. In this graph, it shows the effect of sample K merging when there is burst tail in a window. X-axis shows different sampling frequency. Here is represented as a fraction. Zero fraction indicates AOMG does approximation without sampling. Apparently, it results in very large value error. For 0.99 quantile, from this huge value error, by only exploiting 10% of large value, it achieves low value error. For 0.39 quantile, by sampling half of large value from subwindow, it lowers value error significantly. So you can see sample K merging working properly when there is burst tail. So in conclusion, in data center telemetry streaming analytics, Quantile operation is challenging due to its nature of high throughput, low latency, and low error requirements. We represent AOMG, a new approximate quantile for data center telemetry monitoring. AOMG utilizes online data distribution with new accuracy metric. So we can deliver high performance, low value error, and using low space usage. And it's proven by various data sets with wide range of window size setting. And this is it. Thank you for your listening. For more detailed information, please refer to our full version paper in archive. Thank you.